Good morning, everybody. I'd like to welcome you to the joint G2M Research and NGD Systems Intelligent Storage webinar. My name is Mike Heumann. I am the principal analyst for G2M Research. Just to kind of go through some of the things that we're going to be doing here today, quick view of the agenda. So I'll give some introductory remarks and go through some housekeeping rules. Then I'll talk about an intelligent storage survey that we did about 4 months ago and kind of the results of that, and set the stage for some of the further discussion we'll have. At that point, I'll introduce Scott Shadley, who will be talking about the continuing evolution of storage devices, intelligent systems. And then after that, we'll follow up with about 10 to 15 minutes of audience QA. We'll also have 2 survey questions for you in the audience to answer as we go through the webinar. So with that, let me go ahead and get started. So a couple housekeeping remarks. This webinar will be recorded, both the audio and the video, and we'll make that available to everybody who registered for the webinar early next week. And it'll be available on both the G2M Research and the NGD Systems websites. We'll send out a link to everybody that registered shortly after, probably will be tomorrow. So you can see that and then look at it at your leisure or pass it to other people who you think might be interested. Also, all audience members will be muted during the webinar. If you have questions, and we definitely would like you to ask those questions, please submit them in the Q&A window that you can see. You have the choice to submit them anonymously, or you can submit them with your name. Either way is fine. And then we'll hold those to the end of the webinar and answer those as they kind of go through in order. And if we have ones that are similar, we'll just combine them together. As I said, we'll have a couple poll questions during the webinar just to make sure you all understand. Your answers to those poll questions are anonymous. We're just interested in seeing what the results are from a market research standpoint. We won't cite any particular person's response to that. We might, utilize the overall responses, but that would be it. So with that, let me talk a little bit about G2M Research. So we're a market research firm. We do a variety of things, including publishing reports, holding multi-vendor and vendor-sponsored webinars. We also do a monthly newsletter. Hopefully all of you are getting that. Our focus is on emerging markets in the enterprise IT space, so it's all B2B sorts of things. We do non-volatile memory express is one of the markets we cover, and all of the variety of different devices and systems that fall within that. We also cover endpoint security. And if you would like to purchase the subscription reports, you can go to our website and go on the info button and ask us to contact you about that. One of the things we try to do is do more than just market sizing. We don't just say, here's the size of the market, here are the key vendors. We try to look at what are the big drivers in every given market, and then how do all these things fit together to make a comprehensive picture of the market. I know when I was in the industry, one of the things that really frustrated me trying to do forecasts and things is you'd get different sets of numbers. You'd get, the SSD market was this size, but the NVMe over fabric adapter market was this size, and the two didn't necessarily make sense. They didn't seem to be in sync. So one of the things we try to do is sync all those pieces up so that the picture is consistent and it kind of makes sense across the entire market. So let me talk a little bit about the survey we did. So in November of last year, we did a survey on trends and constraints in the big data market. What we're specifically looking at is for very large data sets. So think of things, 250 gigabytes to petabyte size or greater. Kind of what are some of the problems that people that are using applications around those large data sets see? We had a total of 112 respondents. We did limit the response to either be network storage or application architects or engineers or managers of those people or executives in those organizations that dealt with those large data sizes. There are 4 primary industry sectors that responded. IoT was about a third, big data was another third, hyperscale was about 18%, and then machine learning and AI was another 13% of the total respondents. Annual revenues of the different companies that responded, or the people within those organizations, really it was kind of more or less evenly distributed. About a third were 250 million to a billion. Another third were $1 billion to $10 billion. Then 10 billion or more represent the last group of people. So a good variety of companies of different sizes. And the size of the data stores, as you can kind of see here, went from about 250 gigabytes to 1 petabyte, was a little under half the respondents. Another 30% or 1 petabyte to 5 petabytes was their largest data store size, and then about a little over 20% had data stores that were over 5 petabytes in size. Number of clusters, again, you can see those numbers as well. If you look at kind of the 250 servers or larger, that was really about half the respondents. So, we're talking about fairly large sets of data with fairly large footprints. Some of the results that we got from the survey, and the survey had about 12 questions on it. 52% of people saw that, that very large data sets were a real problem for their organizations, or either today or would be within the next 12 months. And only 21% of people thought current compute and storage architectures could handle what the data sizes would be 5 years from now. About 2/3 of those respondents also thought that smart storage would be a good way of solving this problem. In other words, the ability to process or pre-process data inside storage systems and devices could help solve the problem of moving data back and forth through the network or through servers to the compute nodes. The impact of these big data issues was also fairly interesting. If you look at data movement, 92% of people thought that data movement actually would adversely impact the organization, with about a third, slightly under a third, saying it would limit the way the data can be utilized. In other words, it might take too long to move the data, or it might be too costly. Again, on cost, 62% of people thought that it would impact server networking storage costs, and slightly under half thought it would impact application performance. And you can kind of see the breakdown of these numbers on the right side of the screen. Some of the other findings we had, so we talked about how big of a problem is. You can kind of see here, only 29% of people did not expect that large data set movement would be an issue in the next 5 years. You can see again how many people thought that pre-processing data would help these issues. One of the interesting things is, I think you see a lot of people here that really understand there's a problem in moving large data sets around and kind of making them available for processing. Interestingly enough, only about 40% of people were very familiar with the concepts of intelligent storage, computational storage, in situ processing, or in-memory processing, and those are a family of different technologies. And that's one of the things that really prompted us to go ahead and do this webinar. Looking at these numbers, we thought this is an area where we could certainly help educate people and provide some insight as to how in situ processing and intelligent storage might help them solve some of the big data movement problems they have. And with that, let me go ahead and start our first survey here. Again, if you just go into the Zoom application, you can actually answer the questions. Let me find my mouse here. So I'm going to go ahead and launch the polling. I'll give you a couple minutes to fill this out, and at the end, I'll display the results for everyone. So just go into your Zoom application. You can fill out the questions, and you'll all see the results too. All right, we'll end the polling now, and you should all be able to see the results. And with that, let me introduce Scott Shadley. Scott is the Vice President of Marketing at NGD Systems. Scott's going to talk a little bit about what they see as far as intelligent storage goes, and hopefully give you some insights into that. Scott?
Good morning, everybody. Welcome. Thank you for joining us and taking the time out to learn a little bit about computational storage, making sure here that I've got the screen sharing and can start walking through the process of the deck. So,
yep, we can see you fine.
Perfect. So as Mike mentioned, just a quick blurb. It's always nice to hear a little about who's talking, and of course I finally found a picture of myself I don't mind posting. So I've spent a lot of time in the industry, 20 years. call myself a tech-savvy marketing guy, so the goal here is to be educational and a little bit engineering as well. I've got a double degree in device physics, so NAND and SSD technologies is near and dear to my heart. As far as the lineage of our wonderful team here at NGD Systems, Nader Selessi is our CEO. He co-founded the company with Vladimir and Richard Mataya. I met all three of them when we all worked together at STEC. Bill Haberlin is our Chief Strategy Officer. He's had great success as an executive as well as a CEO of former companies. Al Talavera is our CFO. He helped a lot of other companies as well, from startup to M&A. And Ellie Tiomkin is our VP of Business Development. Again, lots of experience all the way back to the origins of flash products with M Systems through Stack and into companies like StoreOne. So a lot of history here. There's over 250 man-years worth of SSD experience across the team. So while being a startup, we definitely have the capabilities and abilities to produce high-end and significant advantage products to the market. So before I get into what we're doing differently, I wanted to kind of give one quick walkthrough of where the market is today, what we see going on, and what's driving the evolution in the storage needs. So traditional storage, also known as OEM, is still growing, and you can see there on the right that this is showing the OEM growth in the blue boxes, and then the cloud / hyperscale data center, whatever fun name you want to give that segment as, really the significant growth model here. And we could call it even server-based NVMe. Because if you look at taking that red box from the top graph and breaking it out by interface, you can see that it's SATA and NVMe. And today, of course, as we know, SATA, even into last year, SATA was still very prevalent. It's still a driver. There's a lot going on there. It's an infrastructure change to make NVMe successful in the marketplace. But it will have that explosive growth starting later this year and into the NVMe space as we grow on moving forward. Sorry about that. Apparently trying to share just the PowerPoint screen didn't work very well, so I apologize to those watching. However, to kind of back up a little bit of the survey questions that we ran through in the intelligent storage piece of it, this is a different take on it. So our friends at Actual Tech Media did this survey, and they asked the question, what do you see as the most actual or potential for storage performance bottlenecks? And so this is not necessarily looking at what's going on in the storage space as much as it is seeing what's going on with what people feel is causing the performance bottlenecks in that storage. So you have answers like the media storage array, switching, the protocols, so of course, what protocols are causing it, or the applications. And you would think that a lot of people would look at it and say, hey, it's the network because we're doing NVMe over fabrics. Or it's the protocols because we're going to new things like Rocky, getting away from fiber channel, those kinds of definitions. But this survey actually came back with 43% of the people saying that they're concerned about the hard drives, NAND flash, or other medias that they're using to actually make this their storage systems successful. And that's why we see it as a very valuable reason to do something a little different and bring more of an intelligence or an intelligent solution into the storage, because we keep growing data. You can see on the right that data sets are growing larger and larger and larger over time, but the ability to manage that data starts to become challenging. And that's what we looked at as a reason for this concept of computational storage and our in-situ SSDs. So some ideas about talking about what's going on as far as this goes. So as Mike mentioned, big data, large data sets, the different types of data sets, and just the velocity of data we're gaining in this market segment called big data are all drawing to consuming and trying to store data. And that's great. We need to store it. We need to do a lot with it. But then it's a matter of figuring out how to do intelligence on that, getting real-time analytics, the concepts of AI, machine learning, computer vision, all of those are becoming more valuable. Security, of course, is another big one. We've heard a lot in the news recently about our friends at One Hacker Way about having problems around security and data breaches. And cities like the city of Atlanta had a problem last week where they were held captive for a while. These types of things are all based on the ability to manage data more efficiently and keep it secure while you're gaining large data sets. And of course, we always have to look at it from a pricing perspective. There's always going to be a cost factor. Everybody still talks dollar per gigabyte, whether they feel it's appropriate or not. A newer and more valuable asset is the concept of the power footprint and the capacity of that power footprint. So we're starting to, quote unquote, run out of room. There's not an infinite source of power. You can put up all the wind farms you want, you can make all the deals you want, but as you plow down fields to put up data centers, there's got to be power and capability to make that work. And in space-constrained environments like EMEA, the footprint that you're putting that capacity in is becoming even more important. And then what about moving data around? So we know replication is huge. We know virtualizing data is big. But if you get into petabyte data sets and you want to migrate that data, or you want to do something with that data that's just outside the norm of storing it, the cost to get it from point A to point B becomes even more important and valuable. So all of these things are driving what we qualify as a paradigm shift in storage. You can't just store bits anymore. We got to be able to do something with those bits in a more efficient and applicable manner. And a lot of things have happened over the years. The advent of SSDs, we get into SAS, we got 12 gigabit, we got 24 gigabit, then we bring in NVMe, it moves out some of the concepts of a storage controller. But at the end of the day, we still need something different. We need to do something more with our storage. Let the storage work for you. Because at this point, the storage is just storing. I mean, the SSDs are smart in the way that they're managing the data they have on them, but they're not doing anything more than making sure the 0 stays a 0 and the 1 stays a 1. What we're trying to look at now is, what does that mean for us moving forward? So before 2018, NVMe and PCIe drives were available, but they weren't really growing in scale because you had a mismatch of the ability to talk to them. And when we finally get into systems of 16, 17, and into early 18, all the Broadwell-based platforms and things like that could support 4 drives per CPU because of the lanes of traffic that were available in your traditional Intel architecture. And that's great. You're able to add some acceleration to your platform, but you're still not able to do anything with scale. So you're getting faster up front, but you've still got to now start working on this concept of tiering and growing out these large tiered data sets. Do I tier into NVMe and then into SATA SSD or straight to hard drive? And it creates a storage architecture nightmare for people trying to build these systems out and understand really what's going on. So now we look at the current environment, and we've now got the ability to scale the SSD footprint. We've got dual socket systems. We've got much more lanes of traffic through the Intel Purley platform. You even look at the AMD EPYC system, which has even more lanes of traffic. But you still look at it from a perspective that if you're scaling out those NVMe SSDs, you still run into a bandwidth mismatch because you're going to have way too fast on the storage footprint. And if you need to grow it to petabyte scale, you're going to be able to transfer more data, but you can't really do anything with it. You throw in this concept of ME over fabrics, we get a great opportunity to accelerate the sharing of the capacity between the processors, but we're still not doing anything more than just putting the data in a different spot and attacking it from a different point of view. You've got really fast storage, and we've even started slowing down NVMe SSDs. There's no longer really a need in the market for a 1 million IOP drive because you just can't do anything with that. So now we've got cost performance optimized SSDs. We've got platforms that can handle significantly more volume count of NVMe SSDs, but as the capacity and the data sets that we're storing on those, which drives the capacity of those drives goes up, you're still running into a mismatch on what you can do with CPU. And you can now, with NVMe over Fabrics, the whole concept is put a bunch of storage at the top and a whole bunch of pizza boxes with lots of compute. There's still cost involved. Do I need more capacity or do I need more compute? You look at things like the Open Compute project, where it adds in this concept of being able to build out scalable modular architectures in your rack. Again, it's all about trying to help a user balance a CPU versus a storage need, because storage is just data and CPU is where all the compute is. There's something new that needs to happen here. And so what we're doing now is we're taking the intelligence of the processing power of the compute, and we're migrating that out and augmenting the CPU with intelligent storage. And what this allows you to do with this in-situ processing is allows you to slow down, if you will, the amount of processing that has to take place by the host CPU by actually running applications within the storage and bringing harmony back to the bandwidth. Because your CPU footprint, your compute footprint, can stay smaller and more concise, and you're allowed to scale out your storage. And as your storage grows, your ability to process data grows without having to throw more memory at it. In-memory databasing is still valuable. This is definitely not something that solves every workload, but it brings the ability of storage to do more than just simply store bits and maintain bits. we're now actually able to drop applications on the drive and let the drive do the math for you, and then send back just the simple answer or the report out. And it's very modular. There's APIs and SDKs that we use to help make that happen. And it allows you to now bring that harmony that you're looking for. So it's something different. It definitely, there's always questions that come out of it. Is this something that is going to require a lot of change to the architecture, all those types of applications? So what we're trying to do is use that KISS principle, keep it simple, stupid. So it is an NVMe protocol device. It can be used as an SSD and act as any standard NVMe SSD. But at the same time, if you'd like to make it an intelligent product, you simply turn on the in-situ processing power, and you can now augment that storage. It also allows, because of the host agent that runs in the core OS, it allows you the capability to mix and match drives. So if our drive is in with other drives in the system, or you only need computational power for one workload that a user's put on it, you can accelerate that workload, and then you can always turn it back off and use it as a standard drive, or again, mix and match with different vendors. So we're making this very easy to implement without causing a lot of strain on the working environment. So it's cool to see what computational storage looks like, what we're kind of trying to do with it, but I wanted to spend a lot of time in this case talking about use cases and demonstrating how this particular technology works, because it's always cool to talk about it, but it's always even more valuable to see what it can do for you. So when you look at this as far as the workloads that work for this concept, it's IO intensive workloads that are non-disruptive and scalable. So an example would be decompression offload. What if you could actually run the compression engine on the drive and not have to have everything run through memory? So compression is really cool, but getting data back out once it's compressed is always more challenging, because you've got to have somewhere to actually run the algorithm to be able to pull the data back out and put it back in its original form. And if the CPU is trying to compress and uncompress at the same time, you run into a bottleneck. So how about we compress the data, send it down to the drive, and as the drive exits the data out, it uncompresses it or decompresses it as it comes out. We mentioned security as a big deal. So what about encryption and authentication? We all know that data is encryptable today. We have drives that are AES encrypted. We've got TCG-E, TCG-Opal, TCG-Opal Lite, all these different protocols. But again, the drive is managed by a key on the host. So the host is still doing all the work. What if we can move the key management into each of the individual drives, keep it in a secure environment, and reduce the footprint of traffic going through the CPU and processing the CPU has to do simply to make sure the data is real or not? Of course, machine learning, AI, object tracking, this is another very valuable asset, a lot going on in this market space today. What if we are allowing the storage to look through all the data that it's storing, find what you're looking for, and simply report back the answer instead of having to troll through the storage at the processing and memory side to be able to locate and figure out what you're trying to do with that data. And we'll actually show an example of how that works with an in-situ processing SSD. And of course, very simple. When you got to do searches and greps and you're trying to filter information out, there's always a bottleneck. And the bottleneck tends to be trying to look through the data set. Let the data look through itself and report back the answer. These are just a few of the very simple examples of workloads that we can do. And of course, the question out there that we can ask you, and you can throw in the Q&A window, or you can follow up with us later. What do you think? Is there a workload that you see that might work, not work? Again, this is not everything for everybody, and it does have its significant value add in certain spaces, and it has limited value add in other workloads. So it is not something that's going to revolutionarily or evolutionarily change everything about storage, but it's going to make the programs and the platforms and the applications that need it that much more capable. So let's talk about facial recognition. So this is a demonstration, and it has a video, and I did a little test, so hopefully the video should run without an issue. But what you see here on the screen is down here is the host CPU in the system. It's a Xeon processor server that then has 4 in-situ based SSDs placed in it, and you can see those over here. This is the A53 sub coprocessor that's in each of these drives and the workload that's attached to them. And here in the top left, you see 4 windows that are the output files. So what we're going to do with this, as you can see, we had a little bit of fun being politically, having fun with the politics of the world. Back during the Bush and Clinton timeframe, a lot of imagery taken with the two teams or two sets of presidential folks together. So we're going to upload and train into our system onto each of these drives a data set of imagery of all of the different political figures. Once that data set gets uploaded, the system's then going to kick into a facial recognition algorithm and take every image on every drive and tell you who's in that picture. Now the trick to this is watching down here in the bottom left. The CPU is the very valuable resource. This is one tool that CPU and that system is going to be doing, while it could be off running many other applications and workloads. Depending on how busy it is, tells you whether or not it can go off and do something different. If you watch these guys over here on the right, you'll see how we're able to offload all of that processing power into the drives. So right now we're loading pictures into all the different drives, and you can see there is some CPU workload simply to transfer these data sets over. All these pictures are getting pushed to the drives. Now we're going to tell the drives, go find and identify everybody in those pictures. Now look at the bottom left. Absolutely no movement from the CPU. The CPU is just sitting there waiting for the answers. On the right, every one of the drives is sitting there running through the data that's on each of the drives, recognizing who's in those imagery, and outputting the images with the properly recognized individuals. And as you can see here as it's running through, I'll give it a quick stop on one of these pictures here. You'll see that it's grabbing and identifying all of the individuals in the pictures. Oh, I accidentally restarted it. Gotta love when you have tool set application run errors. So as it pulls those data out, you'll see that no matter who's in the picture, one person, multiple people, it's able to identify across the board all of those people in the particular images. Now it's not perfect. It's using everyday normal applications that we have available to us, but it's running those applications within the drive. And as you can see in this last picture, the tool itself even thought that the person in the background was George W. Bush, but it still made sure to clarify the Clintons in front, and even though there's overlap, it would still try to identify the face. But all of that was done over here in these processors. The CPU itself never actually had to do anything to get those answers out of the drives. So this is an example of where facial recognition is able to be run in the drives. The data is actually being managed by the drive controller, and you're doing all of the research, all of the output, and all of the identification without bothering the CPU, so it can go run off and do things with other drives, other applications, or even other workloads. So what about content delivery? So this is the concept we were talking about, security and authentication. So content delivery market is huge. We're driving all kinds of everything. Everybody's streaming everything. We're cutting the cords. But what we think about it from that perspective is, again, data security is important. I'm not so worried about what's going on with the device media itself. I mean, there's value in owning the movie set itself, but what about all the metadata around it? Who's watching which video at what time of day, and all of those metrics that these content delivery people can use to help generate new data content, what videos are interesting to people, what movies, what series they should launch. So in a historical environment, you're reading out your data and it comes and goes. Then what you're going to do is you're going to match the end user with an encryption key, encrypt the data on the CPU, all of this running through the host. And meanwhile, the data is just sitting on the drive doing nothing. It's just being nascent. And then you have to write back encrypted data to the drive before you can actually transmit the data through the host, through the memory, out through the NIC, and to the user. So there's this large data path that's taking place within this content delivery system. So you're able to manage tens of thousands of keys within the compute processor, but you're still slowing things down. You're gating the delivery. You're causing latency issues as you're trying to manage encrypting keys while you're also driving performance and trying to make sure you don't pixelate imagery and things like that. So what if we could do real-time encryption at the drive level and move that key management into the individual drive? What it does for you is now the host CPU issues the read command and information to the computational storage drive, the application running within the drive itself. We do one step in situ drive encryption key and management, so we're able to match the user ID with the encryption key, do all the validation you'd normally do, and instead of having to read and write through the CPU and the host memory system, you're actually able to deliver data directly from the drive out to the end user with a properly authenticated, fully encrypted data set. So what this is doing now is it allows you to drive management of keys inside each drive. And so instead of having one CPU that's managing or hosting hundreds of or even tens of thousands of keys, each individual drive can now manage tens of thousands of keys. And having the SSD talk directly through the delivery path eliminates the need for the host to transpose data out. So this now improves latency on the host and network. You don't have to worry about the key management at the compute layer because the drive's smart enough to do it itself. This allows you to increase output while you're scaling drives and not having to scale the compute resources in the same way. So again, we're reducing the TCO management of the drive and we're adding storage and compute at the same time instead of having to worry about how we can do this scary balancing act of how many processors do I need to deliver 100,000 streams. You can do a lot more intelligent math using intelligent storage. So we also did a presentation last week at the OCP event, Open Compute Project Summit, around Facebook's AI similarity search. So what this process does, and just to give you an example of what's going on here, we put 2 million vectors. So every image that comes into this tool is converted from a JPEG, a PNG, an EPS, doesn't matter what it is. The system uses a Google TensorFlow to convert an image to a vector. Then what Face does is it takes any inputted vector and does analysis to see what the closest nearest neighbor vector looks like. So in this particular instance on this first column, you can see there's a 2 million vector data set on one drive. And we've got the in situ drive loaded but turned off. So there's no processing power being used by the drive. And we can compare an individual vector to 2 million other vectors in about 1 second. And that's going through the entire system on the drive. So then what we're going to do is we're going to say, okay, I'm going to now add another drive. And I'm going to turn on in situ processing. So I've got a total of 2 million vectors split up 1 million on one drive and 500,000 on each of the next drives. You can see that by adding the drives, of course, we're also adding processing power, but we've also turned on the compute capability of the drive itself. We've got a 50% reduction by simply adding one drive to the system and having the drives look and manage the vector analysis within the drive itself. And the power curve, you can see, because we're taking less time and the CPU is not running, we're able to save power and continue down that path. And as we continue to add drives, we continue to reduce the overall response time and the overall power consumption, basically down to the minimum level capable for a given particular platform. So in this case, for 2 million vectors, you can't get any faster than about a quarter of a second response time. And this is using 5 drives. So if we look at it from a scale perspective, this is taking a singular data set, adding drives and reducing response time. The other way to look at this particular application and tool is we can flip that and see how many vectors we can add to the database and still get the equal response time. And so what we did is we took a Xeon CPU, single socket running at 2.2 gigahertz and 32 gig of RAM, and we added up to 24 drives. And with each drive, we effectively got about a 10% smarter search per drive per slot as we increase the data set and increase the number of drives in a system. So now we've got, you can take your choice of an AMD EPYC or a Purley-based 24 drive 2U server, load it up with 24 of these smart drives and literally be able to know that you're getting a fairly linear growth of how much more intelligent your search can be or how much larger your data set can grow without having to throw in GPU acceleration, without having to throw in additional memory or even a second CPU into the system. So from a TCO model perspective, this is a great advantage to users and easily shows how computational storage can add value to a given market segment. So we've talked about what's driving the need for computational storage. I've walked you through some use cases and examples of real actual analytics done by a computational storage device. So then, of course, we've got to kind of start wrapping this up with a conversation about exactly what we're doing and what it is in the way of an in situ SSD. So if you look inside of a drive, you can see here you've got your host CPU, you've got your host memory, your OS, your file systems, your applications. All of these boxes exist in any SSD driver today. You've got your hardware half on the left, you've got your software firmware on the right. So you've got your NVMe front end, you've got your real-time processors, you've got your ECC engine, your AES, all your garbage collection, you've got your FTL, your microcode. all of that. This is what every drive has today. And there's been people, and there are processes and applications where people have tried to use some of these processors to do similar type of in situ processing. What we're doing differently is we're adding a little bit of extra into the controller and into the drive itself in the way of a computational storage processing engine, coprocessors and hardware accelerators. And then on the software side, we have a host API, which allows us to take the application that's running on the host, migrate it down into a form of a container on the drive, so it's isolated and managed within the drive itself. And we use a host driver manager to talk to that host API. And all of that is done over, as you can see, no additional connection to the host. It's all done through the standard NVMe protocol. No rewriting of your kernel, no recompiling. It's simply loading this API into the system, turning it on and saying, go play, and which application do you want to migrate. We provide a GUI with it. It's all got patented application resources behind it. And even with things like at OCP where the project Denali was announced, this is an example of how we're actually able to manage that because we're creating acceleration within the drive and making it more intelligent. So from a perspective of what we have today, you can see on the left side, we've got the in situ processing software. We've got unique firmware management tools within the drive in the way of an elastic FTL. We've got garbage collection and memory management algorithms that help with power consumption on these drives. We have some extremely low power, the lowest dollar per watt, IOP per watt that you can get out of an NVMe drive today. It is a silicon-based architecture, and we also have hardware that has been optimized by our wonderful hardware architecture team led by Rich. Rich has put stuff on Mars, so it's pretty safe to say he knows what he's doing when he builds an optimized hardware set. We have 4 terabyte to 32 terabyte drives today using TLC NAND, and we've got the U.2, and we've got a full height 3/4 length add-in card, all running Gen 3x4. And of course, as we look into the future of what's coming down the road later this fall, we're going to be able to go higher densities as our NAND vendors catch up and give us access to those products. We're going to be moving it to an ASIC-based platform. It's going to be leading as the first computational flash controller at a 14 nanometer process node. And of course, with the ASIC-based platform, we can now bring out the M.2 and even the new form factors that have been being talked about a lot, this EDSFF, Enterprise Data Center Small Form Factor, short, long, wide, medium, you name the variation, again, we can build it. And even if the need is there, we can look at the NF1, which was recently made official from an M.3 through an NGSFF into NF1. And long term, again, the flexibility of this architecture is it's vendor agnostic today. We can do any vendor flash that we want. So our customers, if they want to work a business model where they tell us who to use, it's not a problem. Our controller, our firmware are already manageable around any one of the NAND vendors. We also have scalability. It's not locked into a single tech node. So it's using 3D TLC today. You can go back to planar. You can go forward looking even to QLC or other non-volatile memories. All of those are already built into the platform capabilities of our architecture. So this, again, falls back into the capability to drive scale, flexibility, and computational resources within the drives to allow customers the ultimate flexibility and consumption of the solution. So with that, right about that 15-minute mark, closing down as far as the presentation itself and opening this up for Q&A and seeing what we, if you guys have some questions for us.
And just before that, we're going to launch one more poll really quickly. I'm going to launch it right now. So the question is, how important do you think intelligent storage will be in solving the problems of large data set growth for real-time analytics? We'll give you about 2 minutes to solve this, and then we'll go through the Q&A. Okay, let's go ahead and wrap up the polling. You should be able to see the results here to the poll. And with that, Scott, we've got 3 questions, so let me read these off in order and you can answer them, and then if anybody has any other questions, we can add those in as well.
Absolutely.
So the first question we have is, how does data movement impact predictable time response service level agreements or SLAs for time-sensitive apps?
A very good question. So again, if you look back at the, if we jump back here in the slide deck even to the build out of the architecture that we've created here, you can see that the resources used for making the drive intelligent are not part of the core data transfer path. So if you're wanting to make sure your SLAs, or if you're worried about data transfer as you're moving data in and out, this is completely outside the realm of creating hazards or impacts of data movement. So you can create this containered application management and still move data in and out of the drive as you would historically. So you're going to be still gated only by garbage collection and wear leveling that would kick in with normal applications. And then you can still run computation on the side.
And I think another kind of aspect of the question that perhaps the attendee was asking about is, if you didn't have intelligent storage, how would data movement impact SLAs in that case?
Yeah, again, data move is going to be gated a lot, or basically by what you have in the way of your connectivity. So you have the capability to do all your standard data movement. The ability to move larger data sets is what this is trying to help drive by eliminating the need to actually transfer all that data.
Excellent, thank you. Next question was, is there a cost associated with enabling in situ processing?
So in situ processing itself does contain a licensing. There's multiple packages associated with it. You can do the ongoing so that any improvements or modifications to the tool are pushed at no cost with easy real-time updates, or you can buy it outright in front with the drive, and it's on the orders of a penny, pennies per gigabyte type of a cost associated with making that process available.
Excellent. With three more questions. Third question is, what are the capacities of the M.2 and EDSFF SSDs that your controller supports?
So that's a unique one because it's not necessarily what our controller will support. It is more what the form factor limits us to. So in an M.2, you can get 8 placements in a 22 by 110. So we can do 16 terabytes with today's media technologies, going to QLC and future tech. The controller itself is capable of supporting 256 terabytes of flash in any form factor you can fit that in. So an M.2 with 8 placements is 16 terabytes by the end of this year. EDSFF allows you to double that, so you can get to 32 terabytes of capable storage in those modular form factors. But if you look back at the reason why we still have an add-in card, I can get 128 to upwards of 256 terabytes of capable storage, as the media allows us to fit within those footprints. Okay, and I see next question on the list is, how many of these drives can execute computation in parallel?
That's correct.
The host processing API is associated with each of the controller heads or architecture. So a single CPU, dual CPU, it can run all the drives that are attached to it. So if it's a single 2U server with 24 drives, all 24 can run in parallel. And if you have an NVMe over Fabric type based solution, you have the capability to go even further out across the Fabric network to anything that host API can see, it can manage. There's not a limitation today on the drive count. We've personally, within the NGD systems labs, have gotten it out to about 64 to 100 drives.
Excellent. Okay, and the last two questions we have are related. They're kind of either side of the same coin. One is, are there use cases where computational storage does not work well due to the nature of the algorithms used? And the converse of that is, what applications tend to benefit the most from intelligent storage? Why don't you hit the last one first, then you can kind of hit the ones where it doesn't work as well after that.
Absolutely. So when you look at computational storage and what we're trying to do here, there's always been this paradigm in NVMe or a flash-based product where reads are fast, writes are slow. So if you're going to try to run an intelligent application where you're writing new data into a system, you're still going to be gated by the write capabilities of the flash drive. So this technology is really focused more on being able to look at comparison data, read-centric focused information-based databases and things like that. It's not necessarily focused on the writes of data. So for example, we were talking about compression. Compressing the data into the drive is going to be gated by the drive. The decompression is where we can add value. So that's kind of an example of the benefits come from comparisons, AI type applications, things where you're doing machine learning, where you're having the drive become smart enough about what it's going to report back out. There's even edge processing situations where, if you look at the IoT edge, this new fog market, where you have lower powered CPUs with smaller footprints of storage, being able to accelerate those types of processing applications are very valuable as well. So hopefully that kind of answered both of those questions in one fell swoop.
Very good. Well, everybody, I don't see any more questions. So with that, let me just repeat. We will make the recording of this and the slides from this presentation available to you early next week. We'll send out a link to everybody that registered. Please share it with your friends and anybody else you think might be interested. If you have questions afterwards, you can send them to myself or to Scott. We'll be happy to get back to you and answer them. And with that, let me give you 10 minutes back to your day. And thank you very much for attending. We really appreciate it.
Yes, definitely. Thank you all for your time.